Good morning, students. In this video, we'll discuss about the vector voltmeter. So the main intention of the vector voltmeter is to measure the amplitude of the input signal at two different points in the circuit. Means in a circuit, I would like to calculate the amplitude of a signal. So for that, I'm using the vector voltmeter. So in order to measure the amplitude of the signal which is passing through the circuit, then I'm going to take the measurements at two different points. And also, this meter is used for calculating the phase difference between the two signals which are measured at two different points. Okay, so the vector voltmeter is used for measuring the amplitude of a signal in a particular circuit, and this measurement is done by measuring the signal at two different points in the circuit. And also this meter is used for calculating the phase difference between the two signals which are measured at the two different points. Okay, which are measured at the two different points. This is the main intention of the vector voltmeter. This is the main intention of the vector voltmeter. Let us see the block diagram of the vector voltmeter. If you see the block diagram of the vector voltmeter, so it looks like this. Okay, so this is the block diagram of your vector voltmeter. So here I'm having the two probes. Probe A and the probe B. These two probes are used for measuring the amplitude of the signal, as well as measuring the signal at two different points in the circuit. Two probes are there. These two probes are used for measuring the signal at two different points in the circuit. Okay. Now. So, but in order to measure the amplitude of the signal, what we are doing is whatever the RF signal whatever the RF signal means, I'm imagining that the circuit is carrying the RF signal, and I would like to measure the amplitude of that particular RF signal. And what I'll do is I can't use the RF signal directly in measurement. What I'll do is I'll convert the RF signal which is applied as an input to the probe into the IF signal. IF signal is nothing but the intermediate frequency signal. Okay, now, intermediate frequency signal. So RF signal is a radio frequency signal, and IF signal is a intermediate frequency signal. Okay. So here I'm taking the a probe, and that is measuring the RF signal. The signal range may be from megahertz to gigahertz range, and the same thing is happening in the probe B also. Okay. Now, so these two probes are measuring the values at two different points, and they are giving those inputs to the next level. So before moving further, let us focus on the block diagram of our vector voltmeter. So in this block diagram, if you see this block diagram, the block diagram is divided into five different groups now. So first one is a channel, A channel B RF to, that is a radio frequency to intermediate frequency converter, RF to IF converter. Two RF to IF converters are there. One automatic phase control unit is there, and another one is a vector volt. There is a voltmeter circuit is there to measure the voltage in that particular, that is a voltage in that particular circuit, or I can say that in terms of normal way it is a amplitude of the signal, okay, which we measured. And after that we are having the one more thing called as a phase meter circuit. So phase meter circuit takes a responsibility to calculate the phase difference between the two signals which are measured at the two different points. So totally the internal block diagram of our vector voltmeter, the internal block diagram of our vector voltmeter is having the five major blocks. One is the two are the intermediate frequency, the RF to intermediate frequency converter blocks. One is the automatic phase control unit block. Another one is a voltmeter circuit, which is measuring the voltage and displaying the information on the display, and phase meter to calculate the phase difference between the two signals which are measured at two different points in the circuit, Okay, so now, so if you see this one, as I told you that we are having the RF to IF converter now. So in order to convert the high frequency signal, which is a radio frequency signal, into the intermediate frequency signal. So intermediate frequency signal frequency is a 20 kilohertz. Now remember that it is a 20 kilohertz, 20 20 kilohertz. Okay, it's a intermediate frequency signal is a 20 kilohertz signal. Okay, so means we are converting the high frequency signal, which is in the range of megahertz to gigahertz range, into the 20 kilohertz range. So let us go for the explanation. If you see this one, first of all, in order to convert the radio frequency signal into the intermediate frequency signal, I'm having the sampling circuit and followed by the tuned amplifier. I'm having the sampling circuit followed by the tuned amplifier. This sampling circuit, in order to perform the sampling, we have seen the sample and hold circuit format. Now, we have seen the sample and hold circuit in the what is that second unit S slash H. So just recollect that information. So in the sample and hold circuit, we are having one switch, and that switch is open and closed by the controlling signal. So here I'm having the sampling gate. Now I'm assuming that this gate is acting like a switch, and in order to open and close that particular switch, I'm having one control signal. I'm having one control signal. So here the sampling gate is open and closed based on the control signal, and this signal, this gate takes the responsibility to bring your what is that high frequency signal into the normal frequency signal, and also the tuned amplifier circuit plays a major role. So this particular tuned amplifier circuit is tuned to the 20 kilohertz range. Means this circuit at the output of the sampling gate, we are having the what is it? Intermediate frequency signal, and this particular intermediate frequency signal means this particular intermediate frequency signal is having the different frequency components, but I'm using the tuned amplifier to select a particular 20 kilohertz frequency component. Means in order to choose the fundamental frequency component, I'm using the tuned amplifier circuit, because I told you that the intermediate frequency signal is nothing but the 20 kilohertz signal, which is called as the intermediate frequency signal. So combinedly sampling gate and the tuned amplifier circuit, these two blocks are combinedly acting as a radio frequency to the intermediate frequency converter, RF to IF frequency converter, RF to IF frequency converter. Okay, so now if you take this one, we are having the same configuration. Means this is for the channel A. Na? For the channel B, we have the same thing. For the channel B also, we have the same thing. We have the sampling gate, and we have the what is the tuned amplifier. So at the output of the tuned amplifier, we are having the intermediate frequency. Okay. So but here we are having the control signals for the gating. Na? So we are having the sampling gate, or I can say that it is a simple switch. For the explanation point of view, I'm calling it as a switch. Okay. So we have the control signal. Now this control signal is coming from the automatic phase control unit. This control signal is coming from the automatic phase control unit. Okay. So what exactly this particular automatic phase control unit will do is, this automatic phase control unit will take the responsibility to tune your converter to the 20 kilohertz. Okay, to tune your converter to the 20 kilohertz, and also whatever the IF signal we are getting. See, we are converting the radio frequency signal into the IF signal without changing the characteristics of the radio frequency signal. Means whatever the what is that parameters, whatever the characteristics which are there in the radio frequency signal, the intermediate frequency signal is also following the same characteristics. The intermediate frequency signal is also following the same characteristics. Means I can say that the IF signal is a replica of the RF signal. Only the thing is there is a change in the frequency. Only the thing is there is a change in the frequency. Means whatever the fundamental parameters which are possessed by the RF signal, same fundamental parameters are shown by the IF signal. Only the thing is the frequency is changed. Only the thing is the frequency is changed. Okay. So this automatic phase control unit takes a responsibility to lock to the input signal with certain phase. Okay. So this one takes the what is that phase controlling unit. Means this one take the phase control unit. Means phase control means whatever the IF signal phase is there, it should have the same phase of the RF signal. It should have the same phase of the RF signal. So in order to in order to get the same phase of the IF signal which is there in the RF signal, means in order to in phase the IF signal with the RF signal, what I'm doing is I'm taking the what is that automatic phase control unit. This particular control unit will take a sample of the channel a sample signal of the channel A, which will be given as an input to the automatic phase control unit. Automatic phase control unit. So this particular automatic phase control unit will take the responsibility to accept the two input signal. To accept the two input signal. What is that? One is from the pro channel A, one is from the channel A, another one from the reference circuit, another one from the reference oscillator. So the reference oscillator is a 20 kilohertz one. So the reference oscillator is a 20 kilohertz signal. Okay. So this signal is compared with the a sample of the channel A circuit. A sample of the channel A circuit with the phase control unit. It is just like a PSD. Okay. But when we are comparing these two, obviously we are having the error signal. If at all these two are not matching, then obviously there is a error signal. This error signal is take the responsibility to tune your oscillator. Okay, means we are having the voltage tuned oscillator. I can say that it is a voltage controlled oscillator, what we have seen in the PLL case, VCO, voltage controlled oscillator. So this is the voltage tuned oscillator. Voltage tuned oscillator means after comparison between these two, it is generating one error signal. That error signal is acting as a tuning signal for this particular circuit, so that it is tuned to the particular frequency. It is tuned to a particular frequency, means we are not expecting any difference between the reference signal as well as a signal coming from the what is that, channel A signal coming from the channel A. So this signal is given as an input to the sampling pulse generator, which generates the sampling signals. Okay, now, or I can say that which generates the control signal for the sampling gates of both the channels. Sampling gates of both channels means both channels are working with the same frequency. Or I can same frequency means they are converting the RF signal into the IF signal with the same sampling rate. With the same sampling rate. Okay. So this is about your what is that? This is about your mm, yeah, the process, how exactly the automatic phase control unit will take the responsibility to control the phase. Okay, but initially, let us suppose in the initial case, okay, in the initial case, what I'll do is I don't have any means when you started this particular vector voltmeter to measure the amplitude, in order to log this particular what is that voltage tuned oscillator. In order to log this particular voltage tuned oscillator, what they will do is they'll apply the ramp signal inside this circuit, inside this particular block. They will apply the ramp signal because we should log the what is that voltage tuned oscillator circuit to a particular frequency component. So in order to log that one, what we do is we will take one ramp signal, and that ramp signal is applied as an input to the phase control unit, and which will compare this ramp signal information with the 20 kilohertz reference oscillator. When these two signals, the ramp signal and the reference signal, both are matched at that time, voltage tuned oscillator circuit will enter into the log stage. Once it enter into the log stage in the sense it is carrying the or it is generating the frequency with the 20 kilohertz. It is generating the pulses with a frequency of 20 kilohertz, with a frequency of 20 kilohertz. Okay. So once it enter into the locked stage, what it will do? It will generate the sampling signal, and if at all there is any error, means initially we are applying the ramp signal to enter into the lock stage, but after applying the what is the sampling signals, we have the converter now. So this one is having the different signal, and this different amplitude signal is compared with the input signal again. And if at all there is any error compared to the what is that initial lock stage, that error will take the responsibility, means that error signal, we have the error signal over here, this error signal will take the responsibility to tune this particular voltage tuned oscillator further in such a way that they are locked to the 20 kilohertz frequency as well as in phase with the input signal. Means that I don't think that we have the two different signals. Okay, we have the two different signals with respect to the frequency. We have the two different signals with respect to the frequency, but whatever the characteristics which are carried by the RF signal, same characteristics are carried by the IF signal. Or I can say that the IF signal is same replica of the RF signal except the frequency. Okay, now so now we have the sampling gate which samples the RF signal, and the sample information is passing through the tuned amplifier. The main intention of the tuned amplifier is to select the reference component, that's the fundamental frequency component, which is nothing but a 20 kilohertz. Okay, so fundamental frequency component selected by the tuned oscillator circuit, so tuned amplifier circuit, and this information is given as an input to the amplifier and the limiter circuit. Okay, so means this signal is given as an input to the phase meter. This channel information is given as an input to the phase meter, and this channel information is also given as an input to the phase meter. Means the phase meter is having the two inputs which are measured at the two different points in the circuit. Two different points in the circuit. Okay, so now two different points in the circuit. Wait a minute. Two different points in the circuit. Okay, so now, so here this signal is given as an input to the phase meter. This one is also given as an input to the phase meter. At the same time, the same signal is given as an input to the vector voltmeter. The same signal is given as an input to the vector voltmeter. So this particular vector voltmeter is takes the value from the two different channels and displays the information on the meter. Okay, displays the information on the meter. Okay, so means if you want to measure the what is that voltage at the channel A, sorry, channel A means at one point we are using the channel, means in the circuit we are having the two different points. Let us suppose I'm having one circuit like this. I'm not but okay, if you want to realize this one, I'm having the circuit, I'm not showing the components in the circuit. I'm not showing the components in the circuit. So I use the channel A at this point and I use the channel B at this point, and I would like to measure the amplitude of the signal. Okay, so that is the main intention of this particular vector voltmeter. Okay, so at two different points I'm measuring the value. Okay, at one point I'm using the channel A, and another point I'm using the channel B. So here this vector voltmeter may be connected to the channel A or the channel B signal, and whatever the channel's information you would like to display, that channel information will be displayed on the screen using the vector voltmeter. And the phase meter is the one which takes the responsibility to calculate the phase difference between the signals. Phase difference between the signals. In order to calculate the phase difference between the signals, and in order to get what is that proper information there, this particular phase meter block is shifting the input channel A signal by 60 degrees phase shift. Means by using the 60 degrees phase shifter, it is shifting the what is it measured IF signal to the 60 degrees out of phase. 60 degrees out of phase. Okay, and this block, which is receiving the signal from the channel B, is shifting the signal to the minus 128 phase shifter. Okay, so using the minus one, that is a 128 phase shifter, it is shifting the signal to the 128 degrees out of phase, and it is shifting the signal to the 60 degrees out of phase. Totally, when you are taking the final thing over here, the frequency is not changing, only the phase is shifted. Only the phase is shifted. Okay, frequency is not changing. Remember that point. So finally, what we do is with the help of the these two phase shifters, we are trying to make the 180 degrees phase difference between the two signals. 180 degrees phase difference between the two signals. Okay, 180 degrees phase difference between the two signals. And one more thing is this, in order to calculate the phase difference between the two signals, whether it is a 180 degrees or not, whether those two signals are having the 180 degrees phase difference or not, what I'm doing is I'm converting the what is it sine wave into the pulse wave format. Sine wave into the pulse wave format, or I can say that it is a square wave format. Okay, square wave format. And this particular square wave signal is given as an input to the what is it bistable multivibrator. Square wave signal is given as an input to the bistable multivibrator. Means I'm using the what is it digital phase sensitive detector. I'm using the digital phase sensitive detector to calculate the phase difference between the two signals, phase difference between the two signals. Okay, now so here this one is what is it taking the what we say the phase this is a multi stable sorry bistable multivibrator. This is a bistable multivibrator, and which takes the responsibility to measure the phase difference. And this signal, the measured phase signal, is a voltage signal, right? So here yeah, this particular one is bistable multivibrator. Now, simple cases I can simply say that this bistable multivibrator is acting as a what is it digital phase sensitive detector, digital phase sensitive detector, because we are having the two types of phase sensitive detector. So one is a analog phase sensitive detector, another one is a digital phase sensitive detector, and this one takes a responsibility to measure the phase difference between the two signals, and the measured signal is given as an input to the current switch, because finally the constant current source is the input to this particular switch, which is controlled by the this phase difference signal, and this current source is passing through this particular circuit, and this signal and this signal, these two, wait a minute, I'll show you one thing. Okay, so this constant current source will given as an input to the phase meter through the switch, and this switch is controlled by the bistable multivibrator output, which is acting as a digital phase detector, digital phase detector. So using these pulses and using this input current, whatever the information which is displayed on the displayer, that is nothing but your phase difference between the two signals. That is the phase difference between the two signals which are coming from the channel A and channel B, which are coming from the channel A and channel B. Okay, so the phase meter circuit is take the responsibility, try to make the 180 degrees out of phase between the channel A channel B signals, and also in order to measure the phase difference between the two signals, what it is doing is after phase shift it is converting your signal into the square wave format, sine wave to the square wave, here also sine wave to the square wave, and these square wave signals are compared with by the bistable multivibrator, um, for the phase differences, for the phase difference between the two signals, and the we have the after calculating the phase difference between these signals using the multivibrator, we have some pulses now. These pulses take the responsibility to switch on and switch off the current switch. So whenever the whenever the switch is on, then the constant current will pass through this particular switch and given as an input to the phase meter. Okay, so the phase meter will display the information on the screen which is nothing but the display. So this phase display is nothing but the phase difference between the two signals at two different points. Two signals at the two different points. Are we clear? So this is about your vector voltmeter. So this block is displaying the amplitude signal, and this block is displaying the what is it phase difference between the two signals which are measured at the two different points in the circuit, Okay, so this is a explanation of your vector voltmeter. Okay, so the next thing is, let us go to the another kind of meter, that is a device. Yeah, if you have any queries regarding this one, let me know in the group. Okay, it is a simple thing, but don't get confused with the what is the textbook explanation. Uh, you try to prepare the notes, because if you go more depth, you may get confused. Okay, so the next one is the RF power and voltage measurement meter. So this particular RF power and voltage measurement meter is especially used for what is that measuring the RF signal. The main intention is to measure the RF signal voltage and the power. We are using the RF power and the voltage measurement device. Okay, now, voltage measurement device, which is nothing but this device. Okay, so I'll come to this particular point. So if you see this one, yeah, this particular device is having the two probes. Okay, no, two probes. Okay, so these probes are especially used for what is that to take the sample from the signal, take the sample circuit from the circuit means to whom you would like to calculate the what is that we are interested to calculate the radio frequency amplitude. We are interested to calculate the radio frequency amplitude. So in order to calculate the radio frequency amplitude, we are using the RF power meter, RF power and the voltage measurement meter. Okay, so this what is the use of these probes and what is there in these probes? I'll come to that point later. So RF power voltmeter, the main intention of the RF power meter is what we do is, before going to the RF power meter, let us focus on mm, one thing called as a what exactly the RF signal, right? So we have the RF signal, which is a radio frequency signal, and the radio frequency signal is a very high frequency signal now. The radio frequency signal is a very high frequency signal. So this particular high frequency signal should be, means if you want to measure the radio frequency signal amplitude, uh, if you want to measure the radio frequency signal amplitude, as well as if you want to amplify the radio frequency signal, then whatever the devices which we are using, they are very complex devices now. Okay, so means the complexity in order to analyze and measure the RF signals, whatever the circuit diagrams and whatever the blocks which we are using, they are very difficult. Okay, now so they are very difficult and complex circuits need to be implemented. Complex circuits need to be implemented. So and also in order to convert our radio frequency signal into the normal signal which is nothing but the DC signal, we are supposed to use the rectifiers. We are supposed to use the rectifiers. Okay, so means I would like to measure the voltage, but as a complexity, I would like to measure the voltage as well as I would like to amplify the RF signal. Then whatever the circuits which we are going to use, they are very complex circuit. In order to avoid that particular complexity, what we do is, in order to measure the voltage of this particular RF signal, I am using the rectification concept. Rectification concept in the sense, I will convert the radio frequency signal, which is a high frequency AC signal. High frequency AC signal. I will convert this particular high frequency AC signal into the DC signal. I will convert this particular high frequency AC signal into the DC signal. Okay. Once I convert the AC signal into the DC signal, measuring the voltage of that particular signal is very easy. Measuring the voltage of that particular signal is very easy. But in order to convert the what is that AC signal, high frequency, forget about the frequency, now concentrate on the AC signal, because it is a radio frequency signal is high frequency signal, as we know that, but it is a AC signal. In order to convert the AC signal into the DC signal, we are supposed to use the what is that, rectification. We are supposed to use the rectifiers. Simply I can say that it is a rectifiers. We are supposed to use the rectifiers, right? We are supposed to use the rectifiers. But we know that we are having the different types of we can construct the different types of rectifiers using the normal PN junction diodes. Using the normal PN junction diode. Okay, so when we are using the normal PN junction diode for performing the rectification, for performing the rectification, they can't, means you can't use the normal PN junction diodes. You can't use the normal PN junction diode for rectifiers, in constructing the rectifiers to convert the RF signal into the DC format. Why? Because there are two disadvantages there in your normal rectifier. When you are using the normal PN junction diodes for rectification, there are two drawbacks in the rectification process. So whatever the diodes which we are using, the normal PN junction diodes which we are using in the rectification, they are having the excessive capacitance for the high frequency signal. Okay, it is carrying the excessive capacitance for the high frequency signals. The diodes are having the excessive capacitance for the high frequency signals, and also most of the diodes have the uh, what is it, uh, excessive reverse recovery time. Excessive reverse recovery time. Okay, so in order to measure the radio uh, frequency signal, we are converting the AC signal into the DC format using the rectifiers. But in designing the rectifiers, we are using the normal PN junction diodes. But we can't use the normal PN junction diodes, as there is a drawback when we are using the normal diodes. If you are using the normal diodes in the rectification, for rectifying the high frequency signal, which are the radio frequency signals, then the diodes are having the two different drawbacks. One is the excessive capacitance for the high frequency signal. Excessive capacitance, they are they are giving the excessive capacitance for the radio frequency signal, and also excessive reverse recovery time. Excessive reverse recovery time. Okay, so those two are the drawbacks in using the normal PN junction diode. In order to avoid that particular problem, what are the drawbacks we are having? So in constructing the rectifiers, we are using the two types of diodes. We are using the two different types of diodes. We can use the two different types of diodes. One is the Schottky diode and Schottky barrier. Like I said, that's simply Schottky diode. and another one is a point contact diode. So another one is a point contact diode. Okay, now one is a Schottky diode, another one is a point contact diode. So using the either by using the Schottky diode or the point contact diode, we can rectify the AC signal into the DC format. We can rectify the AC signal into the DC format. We can rectify the AC signal into the DC format. You can't use the normal general P junction diodes as we have the two drawbacks. Okay, now to overcome that one and to rectify the AC into the DC in the perfect manner, we are supposed to use either the Schottky diode or the point contact diode in constructing the rectifiers. Okay, so let us see the how exactly this particular rectification is done. Okay, so how exactly this particular rectification is done. I'll come back to the diagram later. So if you see this one, I'm having the what is that chopper stabilized amplifier and the meter to display the information on the screen. So which is nothing but the RF millivoltmeter. So we are using the probe. We are using the probe in the sense, yeah, we have the probes. So I'm using only one probe. So this probe, what exactly there in this probe? I'll come to that one. After that, we'll come back to this particular measurement. So as I told you that when you would like to what we say the measure the voltage of the RF signal, we should convert the AC into the DC format with the help of the Schottky diode. So this is what the construction I'm having. This is what the construction I'm having to convert the high frequency signal into the that is the RF signal into the DC signal. I'm using the Schottky diode and I'm using the two resistors, and here I'm having the probe which is a measuring element which measures the RF signal, and at the outer of this see, this is a probe which is measuring the signal. This is a probe which is measuring the signal, and this is the Schottky diode which is converting your RF signal into the DC form, and out of this signal is given as an input to the meter to calculate the what is the voltage of that particular signal and display that information on the screen. So same thing is represented over here. Okay. So here, whatever this particular circuit we have now, so in order to convert the radio frequency into that is the AC into the DC form using the Schottky diode, this entire circuit diagram, this entire circuit is integrated as a part of the what is that probe itself. At the tip of the probe, means at the starting point of the probe itself, that the entire circuit is integrated as a part of the probe. This entire circuit is integrated as a part of the probe. Why we are supposed to integrate that entire thing into the as a part of the probe means, because when you are trying to use the probes to connect to the to measure the signal, we are having the communication partner using the probe. We are having the communication path. If at all whatever the wire which we are using, which is not giving the ideal characteristics to drive the RF signal efficiently, from the measuring end to the what is that displaying the device from the measuring end, wherever you are trying to measure the RF signal, from that end to the what is that measuring device, if it is not propagating the signal in the proper way, there would be the some mistakes. Okay, we can't measure the information appropriately. Okay, so to avoid that one means, when the signal is passing through the probe, there might be the noisy signal involvement which may be affect our actual signal measurement. Okay, to overcome that one, uh, what we do is, at the measuring point itself, we are installing or integrating our rectifier, which will convert our measured RF signal into the DC signal, and which can be easily passed through the probe to the meter, passed through the probe to the meter. Whatever the Schottky diode diagram we have seen, that is integrated as a part of this particular block itself. Okay, so this particular block itself, and this end is for measuring the signal, and this is the integrated part. Okay, this one is having the what is it integrated rectifier, and finally we are displaying the information on the screen. So here we are using the probe now. So from the probe we are having the Schottky diode, all those things which is not shown over here. So range switch means what is it what kind of signal we are having, because the signal frequency range is different from because the RF signal is varying from 1 megahertz to the gigahertz range, megahertz to the gigahertz range. So we are using this particular set for the range switch. After that, we are displaying the information on the meter. We are displaying the information on the display. Okay. So this is all about your what is it RF power and voltage measuring device. RF power and the voltage measuring device. Okay. If you are having any queries regarding this one, let me know in the group. So we'll conclude this particular what is it explanation over here. We'll continue in the next class with another topic.